All right, we're going to go into solving quadratics by factoring. So it pulls back in how to factor. We spent all that time on factoring polynomials. We're going to pull this back in to using them to solve quadratics. So we don't want to be spending a lot of time graphing a lot of these, and we know they can get considerably harder, but we still need to be able to solve them or find the roots. So we're going to start with something that's very easy, a level 1. So these are by levels, so you'll see as it progressively goes, they get a little harder. So this one has already been factored for us. It started out, now we've got two factored pairs, and it started out as a trinomial. If we multiply this back, we would get that trinomial. So it's been factored for us. So we have two pairs here. So if we look at our pairs, we have the p plus 8, and then we have this section, the p plus 7. So when we are trying to solve, we have to remember that has to be set equal to 0, and it is, so we know it's in solving form. So to then find the roots, we take each factored pair, so our p plus 8, and we set it equal to 0, and we have p plus 7, and we set it equal to 0. And then we're going to use some simple algebra and solve for the variable. So this would be minus 8, so p is a negative 8. And then minus 7, p is a negative 7. So now our roots are negative 8 and negative 7. Okay, and we've talked about how you can write those. So these are our roots. Now you always want to make sure and plug it back in. So if I plugged in a negative 8 into here, a negative 8 plus an 8 would give me 0. A negative 8 and a positive 7 would give me negative 1. But then negative 1 times 0 gets me 0. So I know it works. The same with negative 7. If I plug this negative 7 back in for the p, I'd have a negative 7 plus 8, I would have a 1. And I'd have a negative 7 plus 7, I'd have a 0. Well, 1 times 0 is 0. So I know both of those work. So you want to state your roots, and you always want to check to make sure that they actually work. This one's pretty simple. So let's go on to another one. So you'll see this one is not as straightforward. It's still factored, but we have other little pieces. We still take each part and we set them equal to 0. So 2a plus 4 is equal to 0, and a minus 9 is equal to 0. Then we're going to solve for each variable. This one has multiple steps, not just a simple easy, but minus 4, minus 4. Those cancel out, and we have 2a is equal to negative 4. And then because we have the a not by itself, just simple equation, divide by 2, a is equal to negative 2. This one, really easy, plus 9, so a is 9. So our roots would be a is 2 and a is 9. This one has two roots, two solutions. If we plug this back in and we had a negative 2 here, a negative 2 and 2 is a negative 4, plus 4 would give me 0. A negative 2 and a negative 9 is going to give me a negative 11, but because I'm multiplying it times 0, I'm going to get 0. Same with 9. 9 times 2 is 18. 18 plus 4 is a 22, but then when I plug the 9 into here, I'm going to get 0, so we know it's going to work. So these are both of our roots. So this is a two-root problem. We know we'd have two roots on our parabola. All right, this one, again, has already been factored for us. However, we see that we pulled out a GCF. If we would multiply this back, this would end up looking like x squared minus 12x. So it's in a factored form here. So we had pulled out a GCF, or the x, first. When we factor, we always remember to do that first. So we set the same way, set them equal to 0. This one's done for us. X is 0. And then we look at the other one, plus 12, x equals 12. So in this case, again, we have two roots, 0 and 12. All right, so this one's a little bit different. We see here that we've had it factored out. We pulled out a GCF of 3, and then we have two pairs here. We've got to set every part equal to 0. So 3 equals 0, x plus 3 equals 0, and x plus 5 equals 0. Well, there is no way ever that 3 is going to equal 0, so that cannot be true. It It cannot be worth 3. So we're not using that as a solution. That cannot happen. Now, minus 3, x is negative 3. Minus 5, x is negative 5. So what it looks like here is I have a negative 3 and a negative 5. I'm going to plug them back in and check. So I'd have 3, negative 3 plus 3, negative 3 plus 5 should equal 0. It's got to make it true to actually work. Well, 3 and a negative 3 give me 0. Well, because this is multiplication and I'm doing anything times 0, I know the whole answer is going to be 0. So that one works. When I plug in a negative 5, again, the same thing's going to happen with my negative 5 and my positive 5 because they're going to cancel out and make 0. I know that because this makes 0 here, multiplying times whatever, I'm still going to get 0. So I have 2 roots here, and those roots are negative 3 and negative 5. I would probably write it as negative 5, negative 3. It doesn't matter in most cases as long as you're stating the roots appropriately, unless it tells you to put them in order. All right, let's go on to level 2. So level 2, you have to factor first yourself. So remember, you always look for the GCF. I don't see a GCF in there. I know that I'm going to go into 2 groups, two sets, 2 binomials. And I know that when I split x squared, I'm going to have an x and an x. And I'm looking for numbers that when I multiply, I get 56. And when I add them together, combine them, I get a negative 1 here. So I have to think about my factors of 56. I know 1 and 56, one of them could be negative, one positive, and so on. And since we know our multiplication, we know this is 7 and 8. And when we look at 7 and 8, we know that the biggest one has to be negative because we need a negative number when we combine those together. It doesn't matter which one you put first. I could do negative 8 and positive 7. And now I've got to level 1 back again, and I set both of these equal to 0. And then I solve. So plus 8. So I get x is 8. And x is negative 7. So this one has 2 roots. You always want to plug it back in and check and make sure it actually works. Sometimes there's little tricky ones that won't work. All right, let's try B. And when you pause the video, try this one and see how you do. All right, so I got my roots here as a equals negative 9 and a equals negative 4. I highlighted in yellow my little step. You must have this step. You must show this step when you're learning. So this is proof that you actually did a process when you're doing this. You're factoring and having this step. All right, let's go on to C here. This is a y squared minus 64. Please pay special attention. This is an easy one to factor without thinking too much about it. This is a difference of squares. This is a perfect square, and this is a perfect square. We know it has to be the difference, not the addition of squares. We know immediately it's going to be y, and the square root of 64 is 8 and 8. And because we need the middle term to cancel, one's going to be negative and one's going to be positive. Then we take... Now we're back down to level 1, and we set these both equal to 0 and solve. And we end up with y is equal to 8 and y is equal to negative 8. Always make sure you plug them in and check. We would have 2 solutions there. Okay. All right, let's go on to D. If we look here at D, I want you to think for a second what you notice that is different from C. We have y squared minus 64 here, and here we have y squared plus 81. This is a perfect square. This is a perfect square, but this is a sum of perfect squares. This is not factorable at this point, okay? This is a prime problem. We can't factor it, so it's a prime problem. So a prime has no real solutions. Okay, so this one's pretty easy. This one's not going to have a root. So when we see ones that are prime, we're not going to have a root. It can still be a parabola, of course, because we know we can plug stuff in and make a parabola, but it has no real solutions. It's not factorable in this format. Okay? All right, so E here, back to a very simple one, but notice that both of my factorable or factors here are exactly the same. I have x plus 2, and if I set it equal to 0, and I do the same thing here and set it equal to 0, obviously I'm going to get the same answer. So minus 2, I'm going to get x is equal to negative 2. Well, I'm going to get the same thing here. That just means that I have one solution, one root. If they're exactly the same, it's hitting in the same spot. So that's going to be one where that vertex is sitting on the x-axis. All right, let's move up to level 3. Level 3 is the most extensive lesson level that you're going to see in this factorable solving quadratics. You always have to remember out to pull a GCF out first. That's one thing that we often forget. So we have to look and see, is there a GCF? Well, in this case, there is. So we're going to pull this out, 4. And then rewrite everything that's left. If I pull out a 4, it's like dividing by 4, I have x squared left. If I pull out a 4, I have negative 3x. And if I pull out a 4, I say how many times can 4 go into negative 16? It can go in there negative 4 times. Now, I'm going to factor, keep going with that middle term. I don't forget my 4 that's out here. So I'm bringing him down. And then I'm factoring, looking for numbers that multiply to get me a negative 4, but then combined get me a negative 3. Well, we know our multiplication tables, it does it pretty easily for us. Then we set every piece equal to 0. We know that 4 is never going to equal 0. So that's not going to be a solution in this sense. But when I put x minus 4 equals 0, plus 4, x does equal 4, not 4 equals 0. Don't confuse that. So that's a root. And then x plus 1 equals 0. I get x is negative 1. Oh, excuse me. Negative 1. So then this here are my roots. Okay, so I want to go back and check those to make sure. Now, if I didn't factor fully, if I didn't fully pull out a GCF, and I started from this point and I started factoring, and maybe I did this, 2x minus 8 and 2x plus 2, and I went from there and I solved, I'm still going to get the same answer. But it's easier, you're not going to make mistakes because you may have a GCF and pull out a variable that could give you another solution. You're not going to have 3 roots. So if you pull something out at the first, your x is going to be the same as one of your other roots. This is quadratic, so it makes a parabola. There's no way that it's going to go across that x-axis 3 times with a quadratic. All right, I want you to try B. B is a 3-star. And mainly because you have to remember that you have to get it in solving form first. And solving form is always when y equals 0. So think about that and then go ahead and see if you can try. Pause the video and see what you can do. All right, so notice here, I had to move over the 20 first. So I had to add the 20 here and add it here and then set it equal to 0. You always want to make sure everything's over to the side and it's set equal to 0. Then I factored and went ahead and set them equal to 0, and I got x is negative 5 and x is negative 4, and I want to go back and check. So this is the hardest you're going to see. The ones with pulling out GCFs or making them set to 0. But it's pretty self-explanatory. After you do a few, it'll make it a lot easier on your practice. So let's do a little procedure chart. Make sure that you ensure that they're solvable first in that solvable form, that you set them equal to 0. So you have to make sure you do that. You're going to look to see, can I pull out a GCF? If possible, always do that first. And then you're going to factor fully using any method of your choice. So if it's perfect squares, if it's difference of squares, if it's one of those very easy type ones to factor, you can use any form or any method that you learned when factoring. You're going to set each factor equal to 0 and solve for the variable. And you'll state those roots, and then you'll check the roots to make sure they actually work. All right, see you next time.